Hello everyone. So welcome to this second lecture of wave. So in this lecture we will talk about the displacement relation in a progressive wave and also the speed of a traveling wave. So let us first start with displacement relation in a progressive wave. As already I have told you in the previous class that the wave may be represented by a differential equation which is like this. This is of course a partial differential equation. So partial means, as already I said, that the dependent variable, which is y, that's a function of two independent variable. That means here it's a function of the space x and time. So that is the reason why this is a partial differential equation, and the solution to this differential equation is given by this relation. In short, this relation itself is known as the displacement relation of a progressive wave. So what this relation actually says is, suppose we have got a wave passing through a medium. In that case, suppose this is a harmonic wave or harmonic function that already we can see. So at any instant of time t, suppose this is the wave which is being represented. Of course, this is the amplitude a, and this is minus a. In this direction we have got y, so this is y is equal to 0 position, and in this case say this is x, and this whole pattern is for some particular instant of time t. As time increases or as time decreases, this wave will shift to right or left. That's a different issue. But at any instant of time t, if this is the wave pattern, in that case what does it actually mean? Suppose there is a transverse wave going through a medium. In that case, these individual points, they depict the position of particles in that medium. Suppose one particle is here, this particle is not at all being displaced. The second particle to this, suppose it is here, this is being displaced to this much. The third particle may be here, which is being displaced this much. The fourth particle may be here. Fifth particle may be again in the mean position. The sixth particle may be displaced in the negative direction to y, so on. So this basically relation shows the displacement of different particles of a medium as the wave progresses through that medium. So essentially this relation itself is known as the displacement relation of a progressive wave. So there is a phase constant phi which has been added to this, which depicts the particle position at some initial time t is equal to 0. We may well choose the phi to be is equal to 0, that the phase of the displacement relation at time t is equal to 0 to be 0. If we choose like that, in that case this relation becomes somewhat like y of xt and a sine of kx minus omega t. In many of the cases we only consider up to this, that is sine of kx minus omega t. The phi we do not consider. So whenever we do not consider phi, you just essentially know that phi is actually equal to 0. However, this solution which we have actually got after solving this differential equation, this is not an unique solution. This is not a unique solution. That means this is not the only solution to this differential equation. There could be other solutions too. And what those other solutions could be? So for example, the sine function that you can see over here, that may be a cosine function, or it could be a combination of sine and cosine. So one such function is represented by this particular formula where I have represented y of xt, that means y as a function of position and time, is represented at some constant a sine of kx minus omega t plus b cos of kx minus omega t. All right, so this is a superposition principle, or rather this is a superposition of sine and cosine terms, and this also gives the solution of a differential equation of a progressive wave. All right, so this solution which I have written over here, or many a times we write this kind of solutions, but just remember that this is not a unique solution. All right, there could be other solutions too, as already I have said. Means the sine term could be a cosine term, or a combination of a linear combination of sine and cosine could also be a solution to this differential equation. Next important topic is angular wave number. Although already we have talked about it in the previous class, but here we will sort of go in a little detail. So let's suppose the solution, as already I have said, that we will drop the function phi or drop the term phi. So it remains that y of xt, that's equal to a sine of kx minus omega t. That is what is my solution to the differential equation of progressive wave. Fine. Or in short, the displacement relation. So what if I put t to be is equal to 0? That means I'm talking about the initial time. So in that case, y becomes x of 0 and a remains as a sine of kx, because this omega t goes off to 0 as t becomes 0. So only up to this much is retained. Now since the sine function repeats itself after every twice pi change in angle, hence I can write sine of kx to be sine of kx plus twice n pi. Now what actually I have meant over here, if you remember the sine cosine circle, if you remember it, that this is a circle which is of unit radius. In this side I wrote sine, in this side I have written cos, then this is angle 0, this is angle pi, this is pi by 2 by the way, this is thrice pi by 2, this is again twice pi, 4 pi, 6 pi, like that, means every twice pi relation comes over here. So the value of sine at this point remains the same. That means sine of 0 is 0, sine of 0 is 0, but sine of twice pi is also 0, sine of 4 pi is also 0, sine of 6 pi is also 0. That means the sine value remains the same after every twice pi change in every twice pi change in angle. So I can write sine of some angle kx, that is to be is equal to sine of kx plus twice pi. Why this n factor is there? It's because I don't know how many twice pi I want to go. Suppose I want to go only twice pi, then n is equal to 1. I want to go to 4 pi, in that case it becomes n is equal to 2. I want to go to 6 pi, in that case n becomes 3. So this n value really changes like 1, 2, 3, 4, 5, and etc. It goes on and on and on. So the sine value doesn't change. So sine of kx can also be written as sine of kx plus twice n pi. These are equivalent statements. So from this particular thing, if I take k common, then I remain with sine of k whole into x plus twice n pi divided by k. So this means that the displacement at x, at any location x, and x plus twice n pi by k are the same. Because if this is the wave, if I talking about this particular position, this wave will not end over here, na? Because this wave will repeat again. This is another cycle of this wave. So in that case, this particular point is having the same phase as this particular point, or the displacement of this point and this point having the same are the same. So what is the angle difference between them? Is twice pi. So what it essentially means that the displacement at any location x and x plus twice n pi of k divided by k are the same. So the difference between two such points is given by x plus twice n pi by k minus of x. So this x and this x gets cancelled. You remain with only twice n pi by k. So this is actually what? This is the distance between any two consecutive, not exactly consecutive, difference between two distances which are having their sign values same. So again what we know? Again we know that the consecutive distance between two points in same phase are known as the wavelength. Now again let's come back. This is a wave. This is one cycle of the wave. This is second cycle of the wave. Now this point, just concentrate on this point and concentrate on this point. These two different points, they have the same phase, because this is one cycle of the wave, 0 to twice pi. From here again, this is twice pi to 4 pi. So this particular point over here and this particular point here over here, they are having the same phases. And as already I have said that this difference is nothing but the wavelength lambda. Crest to crest distance is lambda, or trough to trough distance is also lambda. So how can lambda be also defined as? Lambda can also be defined as the difference in distances between two consecutive points having the same phase. So if the points have to be the consecutive point, then I have to put n to be is equal to 1 in this particular relation. So if I put n to be is equal to 1, this remains as twice pi by k. So that is lambda is equal to twice pi by k. because the distance between two consecutive points in phase are known as the lambda or the wavelength, and again the distance between two consecutive points is equal to twice pi by k. So lambda must be equal to twice pi by k, or conversely I can say k is equal to twice pi by lambda. So this is something, the relation that already I had introduced you to. So physically what does it mean? Physically it means like k is basically a measure of how many waves can be accommodated per unit length of the wave, or per unit distance you can say, because lambda is a measure of the distance. Twice pi is a radian, but often for practical purposes we drop down the radian sign and we write the unit SI unit of k to be meter inverse. But to be more accurate, we should write it actually as radian per meter, but sometimes radian doesn't matter, we write it as just as meter inverse. All right, so this k is known as the angular wave number or propagation constant. Sometimes people also call it the wave vector or propagation vector. All right, so these are various terminologies of the same quantity called k. All right, so k is a very important thing, because whenever we write the solution of differential equation of propagating wave, in that case we introduce it to be a k and omega. We do not write it in terms of lambda or frequency or the velocity. We always write it in terms of the k and the omega, although I can write it in terms of frequencies, wavelength or velocities, but this is a very standard representation. So that is why it is important that we understand k properly. All right, so let's go to the next slide, the speed of a traveling wave. This is very important, that what do we mean by the speed of a wave. So there are a lot of things written over here. I will not go into that. I will simply draw your attention to this particular wave. Let us consider this is the status of the wave. This is, let me designate it to be 1 and this to be 2. So 1 is the status of the wave at some time t, and 2 is the status of the wave at some time say t plus delta t. That means in a difference of time delta t, this wave has traveled a distance delta x. So this distance is delta x. So what could be the velocity? We know velocity means the distance traveled per unit time. So this is the wave velocity. But how do we get an expression of delta x upon delta t? In order to get that, we must consider that any particular point in a wave, let us consider this particular point. So this particular point, whenever it is shifted from this location to this location, its phase remains constant. Let's consider the phase of this particular point to be pi by 2. Then whenever the wave is shifted through a distance of delta x, this particular point has got the same phase pi by 2. And this is true for any other point. If you talk about this particular point, this also has got the same phase whenever it reaches a distance delta x. So what we can say, that as the wave propagates, the phase of the wave doesn't change, or it remains as constant quantity. So since the solution of a wave is given by say y is equal to a sine of some kx minus omega t, so this part is known as the phase, and this phase remains constant. So I can write simply as kx minus omega t to be equal to constant. If it is a constant, let me first take the derivative with time. Then this is kx minus omega t, and in this side also I will take a derivative ddt of constant. But ddt of constant is actually 0, because first order derivative of any quantity which is a constant with respect to another quantity is always 0. Derivative of a constant is always 0. So if you derive this, what you will get, k is anyway constant, this comes out of the derivative sign, it becomes dx dt minus omega is another constant, then I have dt t of t, that's equal to 0, but this is equal to 1 because dt upon dt, so that should go as 1. So I remain with k dx by dt minus of omega, that's equal to 0. I can write dx by dt to be is equal to omega. Just take omega into this side and divide it by k. This is nothing but the velocity of the wave, because dx dt already we have evaluated and velocity of the wave is already given by the dx dt. So uh, this quantity omega by k, or the ratio of angular frequency to the angular wave number, that gives you the velocity of the wave. In short, what is omega by the way? Omega is equal to twice pi nu, already we know that, and k is equal to twice pi by lambda. So this twice pi gets cancelled, lambda goes up and it becomes nu lambda. So this is something that already we have got in our class 10, that velocity of a wave, propagating wave, is nothing but nu lambda. Okay, so this relation and this relation, they are but the same relation, only the representation is little different this time in HS classes. Otherwise, in already metric level, we have got this relation that v is equal to nu lambda. Frequency of the wave multiplied by the wavelength of the wave gives you the velocity of the wave. This is a very well known relation. But here we will remember this relation. Along with that, we shall remember one more relation, that the ratio of angular frequency to the angular wave number gives the velocity of the wave. And how actually we have derived it? We have derived it by considering the phase of the wave to be a constant and taking a time derivative of it. Alright. So I have just written over here taking a time derivative or differentiating with time. I have written little direct. If you have difficulty in understanding, then please follow this particular thing. This particular part you please follow. Make your note. Alright. Okay, so let's move on. Particle velocity and wave velocity. So wave velocity we have now understood. Now let us try to understand what is meant by particle velocity. So interestingly, see, once again we start with the same relation, the displacement relation, y is equal to a sine of kx minus omega t. So in this case, wave velocity is given by dx dt, as already we have got in the previous slide. Particle velocity, capital V say, will be given by dy dt, because y is the displacement of particles of the medium. So particle velocity, if I have to know, then I must take the first order derivative with time of this quantity y. So if I just take it, in that case what I shall get? I shall get a omega cos of kx minus omega t. How do we get it, by the way? Dy dt, say a is anyway constant, so it remains here. I have to take ddt of sine of kx minus omega t. So a remains as a because this is constant. Ddt of sine, so first order derivative of sine, it should give you cosine. So cos of kx minus omega t, but this part is not time, so I have to again take a differentiation of this. All right, but in this case I have only time part over here, so ddt of dy dt is equal to a cos of kx minus omega t. uh, I'll remain with a negative sign, say in this case if I derive it, then I shall remain with a minus of omega term. So it should give me a minus of a omega cos of kx minus omega t. All right, so this negative sign should come over here. There should be a negative sign because I have got it from this particular relation, deriving it with respect to time t. So if you just take the magnitude of it, in that case the particle velocity varies with time from a minimum value 0 to a maximum value a omega. So if you just consider the maximum value a omega, in that case you will remain with v is equal to a omega, or in terms of omega you can write a is equal to a into twice pi nu, the frequency of the wave of course, then twice pi a, I have clubbed these terms together, and a nu I have written it to be v by lambda. So as I have put over here, so it becomes twice by a by lambda into v. So this is basically the relation between the wave velocity v and the particle velocity capital V. All right. So that's a new relationship that already we have got. Okay. So um, let me write it. Next, let us go to the next slide. In that case, we know this is something like visualizing the velocity, wave velocity. How exactly you can visualize the wave velocity? So we know the displacement of particles of a medium is depicted by the equation y of x t is equal to a sine of kx minus omega t. We could also write as a sine of omega t minus kx, because nobody bound me to write it as kx minus omega t only. I could have just altered these positions. I could write it to be omega t minus kx. So why I don't write it? Or if I write it, what is the change that I'll look? Similarly, I could write y is equal to a sine of omega t plus kx or kx plus omega t. So these are different possibilities of writing the solution to the wave equation. How visually they are different? Let us see it. So please note these waveforms. Here you see this is y1 is equal to a sine of kx minus omega t. The wave is moving towards right. But in this case, I have written y2 is equal to a sine of kx plus omega t. The wave is moving towards left. Alright, if you see it carefully, you can distinguish this very easily. So if I write this and this basically I have written it to be y1 and this I have written it to be y2 in the picture. How would you know in that case that this wave should go from left to right or in the positive x direction, and this particular wave should go from right to left or in the negative y direction? This is given by the constancy of phase, because we know the phase constancy gives us the velocity of the wave. If you just take the time derivative of this phase, so if I just write kx minus omega t to be is equal to constant and take a time derivative, then I will get k dx dt minus of omega to be equal to 0, because ddt of constant equal to 0. So dx dt becomes equal to omega by k, which is a positive quantity. So whenever you write kx minus omega t, there is a negative sign in between. Wave moves in the positive x direction because this is the velocity. On the other hand, if you write kx plus omega t to be equal to constant, in that case, if you derive it with time, you will get k dx dt to be plus omega, that's to be equal to 0, or dx of dt is equal to minus of omega by k. So there is a negative sign appears. So the wave must go from right to left or in the negative x direction. The same thing exactly you can see in this particular figure. So in this case, the wave is moving towards left, this wave is moving towards right, and their expressions are given as already we have proved here. And writing this omega t minus kx means I have been writing at kx minus omega t. If you write omega t minus kx, it doesn't change anything else, but it will change the velocity of the particle, initial velocity of the particle, that will change, because otherwise there will nothing will be changed in terms of velocity of the wave. Why? Because even if you take a derivative, suppose I write it, say omega t minus of kx equal to constant. If you take a time derivative, you remain with omega minus k dx dt, that's to be equal to 0, or dx dt even then becomes omega by k, which is same as this. So it doesn't make any difference. Wave will always propagate in the positive x direction. Where you will see the change, you will see the change whenever you take the time derivative of y. That means you will find the velocity of the particle and you will write dy dt, that will give you a cos of omega t minus kx into omega, or I can write to be a omega cos of omega t minus kx. The same thing in the previous slide, we have got it to be minus of a omega. Why? Because there was a kx minus omega t. I just go back for a while. Here you see I just put an additional negative sign over here, because from this particular derivation already we have got there is a negative sign. All right. So that is the only difference you get if you write it to be kx minus omega t or omega t minus kx. All right. But there is nothing changeable in terms of the velocity of the wave. All right. So that's all I have in this particular lecture today. In subsequent lectures, we will talk about the superposition principles, the interference of waves, the formation of beats, etc. And for this particular code, this is generated in MATLAB by doing programming in MATLAB actually. So the code is given over here. If you are interested, in that case, you can just type this code in your MATLAB routine and check it for yourself. All right. So thank you so much.